Hello.
Hello, guys. Nice to see you. How are you doing?
Fine, and you?
Okay, not bad. Good afternoon.
Good afternoon.
Hi.
How are you doing?
Doing okay. Thank you. How are you?
Yeah, I'm pretty good.
That's nice. Okay. During last discussion, we considered this, I've proven the parallel axis theorem, and which gives us an opportunity to calculate moment of inertia when the moment of inertia with respect to the center of mass is known, which is quite useful application of this theorem could be. And also we discussed in details the rotating rigid body, which combines both translational and rotational motions. So we have shown that it's necessary to consider two components of kinetic energy of such motion associated with translational and rotational motions. So that implies some additional considerations when we want to calculate, for instance, velocity of the center of mass of translational motion of a rigid object rolling down from inclined plane. So also part of this initial potential energy should be transformed in the kinetic energy of translational motion. So now we continue with the study of rigid object rotational motion, and we will introduce here during this discussion concept of torque, which is equivalent of force for rotational motion, and also such important parameter as angular such concept as angular momentum. So equivalent of linear momentum, obviously, for rotational motion. Okay, so with this, we will proceed to my other screen where we can write. And let us start with the torque. So torque is, as I mentioned, equivalent of force, and it just shows us what will be the effect of applied force on rotational motion with respect to about some axis of rotation. So as a model system, let us consider a bolt with some center O. Here will be our axis X, and we will have some range. So now let us consider that at the edge of this range, there is some force F exerted with some angle phi with respect to axis X. So in order to describe, quantify the effect of this force on rotation of this system about axis, which goes through point O, we need to introduce a new parameter, which is torque, and it is equal to radius, distance from the origin to the point where this force is exerted, times force times sinus and angle, no, it's not alpha, it's phi, angle phi. So in other words, we can also extrapolate this line along x force vector. And when we build a perpendicular from the origin about which rotation should happen, we get some segment like D is perpendicular to this line. And we can write that this will be equal force times D. So D is R times sinus theta, and it's called moment arm or lever arm of force F with respect to this origin point O. So actually what matters, this lever arm and magnitude of force. And lever arm or moment arm is defined by orientation of the position vector of this point where force is exerted with respect to the origin about which this rotation tends to happen under the effect of this applied force, and of course orientation of this force. So torque is a vector quantity and is defined as the vector product of position vector and force vector. So if we have, for instance, three-dimensional space x, y, z, and here is some point where force F, if exerted, here is position vector R. Between these guys, we have some angle P. So the torque vector will be aligned along axis Z perpendicular to the plane where vector R and vector F are aligned. Torque. And its magnitude is defined as product of magnitudes of position vector, force vector, and sinus phi between these two vectors. So units of torque are Newton times meter. So please don't confuse with work because it also Newton times meter, but here it has completely different physical meaning because it shows what is the effect of exerted force on rotation of the body where it's exerted on with respect to certain axis of rotation. So if we have more than one force exerted, for instance, let me maybe clean this part. We have some rigid body. Let's consider this point as a point through which the axis of rotation is passing perpendicularly to the plane of the figure. And we have two forces exerted on this rigid body. So it's force F, and here is force F1, and here is force F2. So then if we extrapolate these lines and build our perpendiculars to these lines which go through the force vectors. So here is right angle and here is right angle. So this will be D1, this will be D2, lever arm 1 and lever arm 2. So now we see that force F1 tends to rotate this rigid body in the counterclockwise direction. However, force F2 tends to rotate it in the clockwise direction. So they counteract with each other, these torques which are created by these forces F1 and F2 with respect to origin O. And we need to deal with some net force, net torque. So net torque will be torque 1 plus torque 2. And since these both torques tend to rotate the body in different directions, then here should be F1 times D1 minus F2 times D2. So we define some direction as positive, some negative, and then we have kind of difference. We calculate the net torque exerted on this rigid body. So let us consider in more details the rotation of rigid body under some torque in order to find the relationship between external torque, like net torque applied to rigid body, its moment of inertia, and some kinematic parameters like angular acceleration. So for this purpose, let us again consider some rigid body. Here will be our origin. We have a system of coordinates, X and Y. Let us consider some small element with a mass dm on this rigid body and some tangential force, like small tangential force, Ft, which is applied to this element of the rigid body. Why tangential? Because if it rotates, if the rigid body rotates about axis which goes through the origin O, then this will be some circular trajectory of this particular small element with the mass dm, and this force is aligned with the tangent to the circular trajectory in a given moment of position of this mass. So we know from previous discussions that if we have some force exerted on body, there is some acceleration. So in this particular case, it will be also tangential acceleration because we have tangential force. So it means that tangential acceleration is acceleration originated from the change of the magnitude of velocity vector, not its orientation. So when it's a change of orientation, it's centripetal acceleration. So we have dft, we can express it in dm according to second law of motion times at, this small element mass dm times its tangential acceleration. Now we want to use our new parameter introduced, net torque. So let us call dt external. It means next net external torque exerted on this small element dm will be equal to the radius vector, like this r, times force dft. Since it's tangential force, then it will be always right angle between these two vectors, and means that sinus of 90 degrees will be unity. So we don't write sinus anymore. Here will be just radius times dft. And now we can substitute, instead of this force expression in terms of mass and tangential acceleration. So it will be AT times R times dm. Okay, now we need to recall how tangential acceleration is connected with angular acceleration of the rigid body. So linear velocity is equal to radius times omega, angular velocity, and tangential accelerations is dv over dt, and this is equal to r times d omega over dt. And this is nothing else as angular acceleration alpha. So we have radius times alpha. So now we can substitute it here and write for this small net torque exerted on small element dm with respect to the origin. It will be equal to alpha r squared times dm. Okay, obviously if we want to calculate the total net torque exerted on the body, so we need to integrate this expression for all parts of this rigid body. So then tau external, let's call it like some resultant total, it will be integral alpha times r squared dm. Since alpha is angular acceleration and we deal with a rigid object, means if small element dm is moving with certain angular acceleration, that automatically means that all other parts of this body will move with the same angular acceleration. So we can take it out from the integral. It will be r squared times dm. And this part you already see, this is moment of inertia. And in this particular case, it should be moment of inertia with respect to this origin O, the axis which goes through the origin O. But we can write in general just moment of inertia because it could be any arbitrary point considered as origin. So we can write that the total external torque on a rigid body with respect to certain axis origin will be equal to its moment of inertia times angular acceleration. So this is the relationship between torque and parameters of the rotating rigid body, moment of inertia with respect to certain axis of rotation, and angular acceleration. So that is technically second law of motion, but in terms of parameters which describe rotational motion of rigid bodies.
Professor, excuse me, I have a question.
Sure.
Why is torque called external? Is it because it's caused by external forces or what?
Yes, yes, you are absolutely right. This, if we have external forces exerted on the rigid body, they automatically create this external torque with respect to some origin.
Okay, thank you very much.
You're welcome.
May I ask?
Yes, sure.
I'm a little bit confused. Is it a separate task?
Can you repeat your question, please?
Is it a separate task? The last slide, the current slide.
You mean separate task for what? It's we on this last slide we show the relationship between the net external torque and kinematic property of kinematic parameter of angular acceleration and the coefficient which should be used. We show that this is moment of inertia. So moment of inertia times angular acceleration gives us net external torque. So I guess I didn't understand what was the question. Okay. Now we, if you can formulate it in more clear way, you're also welcome to ask me later. But this is just part of explanation, the relationship between this new parameter torque with previously introduced parameters of moment of inertia and angular acceleration. So in particular, it's called rigid body rotation under some net external torque. At this point, we can proceed further and introduce another important parameter which describes rotational motion is angular momentum. So angular momentum is equivalent of linear momentum. So we remember from previous discussions when we introduced linear momentum is mass times linear velocity. And we could also get some net external force as first derivative of linear momentum over time. So it's equal to the rate of changing linear momentum. Angular momentum is also a vector quantity, and it's a bit different. So let us highlight it here. Then linear momentum x, y, z. So if we have some body moving with some linear momentum p, and here is mass of this body. So here is position vector r. Here is some angle phi between these two vectors. So angular momentum, as similar to the torque, will be given as a vector product of position vector and linear momentum vector. So it will be also perpendicular to the plane where position vector and linear momentum vectors are aligned. So now let us consider the relationship between net external torque and change in angular momentum. So we see here we have this relationship between external force and change of like rate of the changing the linear momentum. So something similar we should get also for angular momentum and torque. So from previous slide, we know that torque, net torque, is equal to the radius vector product of position vector, radius vector, to the net force. And this can be represented as radius vector times first derivative of the linear momentum vector over time. So now let us do some manipulation and add another vector product here. So add dr over dt times linear momentum vector. So why we can add this? Because this vector product is equal to 0. So any ideas you guys have why this vector product is equal to 0?
Angle between them, maybe.
Yeah, something like that. So here we can write that, sorry, this derivative is velocity vector, and then it's times linear momentum vector. And we know that velocity vector is parallel to linear momentum vector, and that means that the vector product of vectors which are parallel to each other will be equal to 0. So you are right. And that means that we can add or subtract this. It doesn't matter because it will not change anything. So now we can write again. Maybe we can continue here. So, oops. Let's clean this part. We can write that it's equal to 0 here. And this will be equal. So we have, if we take into account rules for taking derivatives of vector products of two functions, like we have position vector and linear momentum vector. So then we can write that this will be equal to first derivative of the vector product of position vector, linear momentum vector over time. So this here in the numerator is some interesting new parameter, which is the angular momentum. So we can write here dl. So we substitute this vector product with the angular momentum over dt. So here now we get similar equation as previous one for force and linear momentum, but now it's for rotational motion. We can write the total net torque exerted on the rigid body will be equal to the rate of changing the angular momentum of this rigid body. The units for angular momentum is kilogram times meter squared divided by second. And if total, if we want to calculate total change of angular momentum, delta L total, that should be integral of the sum of all torques, like some net external torque, dt. So assuming that this net external torque may change with time, if it's not constant, then we need to integrate, obviously. And that means that the change of angular momentum is equal to the angular impulse of external torque, net external torque, which is similar to what we discussed previously, that change of linear momentum is equal to the impulse of the net external force. So here it's the same concept, but different parameters which are used. So now let us consider in more details angular momentum of a rotating rigid object and find the relationship between the moment of inertia and some kinematic parameters of rotating rigid object, like angular velocity and angular acceleration. So for this purpose, we consider such a system. Let us consider a disk. So it's some symmetric body, and our axis of rotation will go through the center. So axis Z. So rotation. This disk is rotating about this axis, and here will be our angular velocity vector. So now we can pick up some point. Let's call it mi, with mass mi, on this disk. It will be at the distance r from the origin, or from the center of this disk, and here will be this circular trajectory of this element mi while the disk is rotating about axis z. Here will be some linear velocity vector vi, and we can calculate angular momentum of this small element with respect to axis z. So Li will be equal to mi times vi times ri. So we have, here is our pi, linear momentum. Here is our position vector. And since here we have right angle, because linear velocity vector is always tangential to the trajectory, so it's always right angle to the position vector. We don't have any sinus phi, because that is equal to 0. So now let us express vi in terms of ri and omega. It's a rigid body, so we don't have this index I next to omega, because any point of this body will move with the same angular velocity. So when we substitute it instead of vi, we will get mi times ri times ri times omega. So that is equal to mi ri squared times omega. Now, if we want to calculate the total angular momentum with all this rotating disk about axis z, we need to sum up all angular momentum of all points which form this disk. So that will be sum of all these angular momenta, and it will be mi ri squared times omega. Omega without index, because it's the same for all points. And this part is nothing else as the moment of inertia. So moment of inertia with respect to this axis z. So that is equal to I z times omega. So here we have a relationship between rigid rotating object, angular momentum of this rigid rotating object, and its moment of inertia and kinematic parameter, angular velocity. Now, if we go one more step further, we will get the relationship also with the angular acceleration. So let us take the derivative of this total angular momentum over time. This will be equal to moment of inertia times d omega over dt. So we see that change, like rate of changing the angular momentum over time, is equal to the product of moment of inertia with respect to the axis about which the rotation is happening, and angular acceleration alpha. And we know from already from previous discussion in today's lecture that this is equal to the sum of all torque applied to the exerted to the rigid body. So it will be equal to some net external torque. Now, if we have some isolated system, for instance, and external torque is equal to 0, because for isolated system, all net forces, external forces are equal to 0. So automatically that means that net external torque is also equal to 0. Then dl over dt is also equal to 0. Means that L total of isolated system is equal to some constant. Means that similar to the linear momentum vector, angular momentum also stays constant in isolated system, means that we have some conservation of angular momentum. And this conservation of angular momentum can be very useful for different applications in solving problems. For instance, let us consider some case. It's quite classical example, but we'll highlight how this can be used in life. So we know that L is equal to I times omega. Angular momentum is equal to the product of moment of inertia times angular velocity. So we also know about this conservation of angular momentum, means that if we have some initial angular, initial case stage of the system, we have some initial moment of inertia times initial angular velocity. That will be equal to product of final moment of inertia when we change the shape of the body or some mass distribution inside the body times final angular velocity. So it means that if we change the moment of inertia, automatically it will result in changing the angular velocity. So now if we consider some star before supernova exposure, we have radius of a star, which is quite large. Then this transformation is happening with minimum change of the mass. So we can consider mass as constant. And then it transforms to some neutron star with very small radius r. Obviously, because of such transformation, the angular velocity should change dramatically, because r is much larger than initial radius is much larger than final radius. So if, for instance, we know initial period of rotation, so how much it takes for the star to rotate about its axis of rotation to make full rotation, then we kind of want to figure out what will be the final period of rotation for the neutron star. We know that moment of inertia of a sphere is 2/5 times total mass times radius in second power when it goes through the center rotation, about the axis which goes through the center of this sphere. Then for omega, we can write 2 pi divided by t initial. 2 pi divided by period of rotation gives us angular velocity. So that should be, according to the conservation of angular momentum, should be equal to 2/5 total mass, which didn't change, times r squared radius of the neutron star. And in this case, we need to also multiply by 2 pi divided by t final. So now we can cancel out this and this. We can also cancel this 2 pi, and we get a simple relationship between final period of rotation and initial period of rotation, which is radius of the neutron star divided by the radius of the normal star before transformation, squared times initial period of rotation. Since neutron star radius is much smaller than the normal star before transformation, this period of rotation of a neutron star will be much shorter than period of rotation of the initial, like star of the initial stage of its condition. So means that the angular velocity of neutron star will be much higher, because angular velocity is 2 pi over t. Okay, so this is some classical example of this application of angular momentum conservation. So any questions, guys?
No.
Yeah, in this discussion, we introduced first the torque, which is equivalent of force for rotational motion. Have shown how this net torque exerted on a rigid body is related to moment of inertia about axis of rotation, like some given axis of rotation, and angular acceleration. Also, we introduced angular momentum, which is equivalent of linear momentum in rotational moment, rotational motion. Have shown the relationship between the between the angular momentum and moment of inertia with angular velocity. So the product of moment of inertia is with angular velocity gives us the angular momentum. Also have shown that the net torque exerted on a rigid body is defined as the rate of changing angular momentum vector over time. And also highlighted that for the isolated system, when net torque is equal to 0, the angular momentum stays constant, means we have conservation of angular momentum. And that could be applied for different cases when the rotation of rigid bodies is considered. Okay, thank you very much for your attention. Have a good weekend. Take care and see you on Monday when we will start to discuss a new topic, which is gravitation.
Thank you very much.
Thank you.
Okay, thank you. Bye-bye.
Thank you.
Goodbye.
Bye.